We're going to do 3 examples. And sort of one of each type. And as always with applications, sometimes it's basically the same, but sometimes the numbers are a little bit less friendly. They can be a little bit more wonky, or there are a couple of little things that are just worth making sure you've seen this before and done it once before. It's not particularly hard, but if it was your first time ever doing it, was on a test, there are some things that might trip people up. So the height in meters of a corn stalk is modeled by the function h at t, where t is time in months after the seed was planted. H is in meters, t is in months. Thinking about units is another part of this, right? You got to make sure that you can actually do that part yourself and answer the question yourself and all that. Question A, determine the average rate of change. So average rate of change, we're going to use this slope formula from grade 9. Average rate of change will be h at 3 minus, thank you, h at 1 over 3 minus 1. So we need to go get h at 3 and h at 1. And there's a bit of messy fraction work, but of course, if you're just using your calculator, it's still pretty easy. So I believe this works out to 10 over 21, all divided by 2, which is 5 over 21. And what does that mean? So I wrote it out as a decimal. The fraction answer, I think, is the one that we would want in this case, but I wrote it as a decimal just to help think about it. So, and one trick that you can use for thinking about, I think we talked about this on Friday, but for thinking about units is, I'm not even sketching, I'm just drawing the axes to label. So this is height, and this is time. Height is in meters. Time is in months. Months, yep. So meters per month. So from month 1 to month 3, that's 2 months. It grew an average of 0.238 meters per month. Easy enough, right? I hope. So therefore, B, determine the instantaneous rate of change after 2 months. So that's right in the middle of 1 and 3. Isn't it? So h of 2 is 4 over 9. So I get t squared over 5 plus t squared minus 4 over 9 all over t minus 2. Yeah. Oh gosh, yes, of course we do. Where's my head at? I'm going to have to squeeze it in. Limit as t approaches 2. equals the limit as t approaches 2. Thank you. You can go ahead and solve. You don't have to wait for me. Hopefully you know what to do. What would we do here, Isaac? No. Yep. So yeah, like you could either get a common denominator on top, or you can do it this way. So I have to multiply by both denominators. So 9 times 5 plus t squared over 9 times 5 plus t squared, like that, right? So go ahead and try that. So when you do this, I multiply this fraction by 9 times 5 plus t squared, which cancels the 5 plus t squared, so it's just 9t squared. So that's what I got there for multiplying by the first fraction. And the second fraction is 4 over 9 times this, so the 9's cancel, and I get 4 times the other bracket that's left. Is that still frozen? Okay. So 4 over 9 times this, the 9's cancel, and I get that. And then I'm just going to simplify on top. I think I've said this a bunch of times, but you know, as you're working through this, you might not see how it's actually going to cancel. You might be worried you've done something wrong, but you got to follow it through. You got to know that it's going to work out every time. And I mean, if you get to the final step and you've done something wrong, then that's another story. But at this stage, I wouldn't be worried about that. I would be just simplifying it and having confidence and faith that it's going to work out. So this works out to 5t squared minus 20, because you get a couple of t squared terms on top. And I hope you notice that there's a common factor on top, and then it works out to a difference of squares. And there's this, whoop, I ran out of space here. There's this great check that happens automatically in every one of these questions where you get the t minus 2. Like if you got here and you found this factor that divides, I don't see how you can make a mistake and have that happen, right? If you got this, I gotta think you've done it correctly. Because if you made any algebra mistakes, it's very unlikely that this would still factor and work out that way. All right, so this is the limit as t approaches 2 of 5 times t plus 2 over 9, 5 plus t squared. Oops. 9. And I think that works out to 20 over 81. And that is approximately, I don't, like sometimes something sort of interesting, I mean, not really interesting, but if I think about this, 0.247, it's a bit bigger than the average. So at month 2, it was at that moment of month 2, the instantaneous rate of change was higher than the average over the course of the other 2 months. Again, that might be something, depending on your point of doing all of this, that you might be interested in. Or when was it growing the fastest? Like, there's all other kinds of questions that you can start to explore and ask that we won't get to in this course, but you may have realized that that's kind of where some of this is going. You can get a lot of really useful information from this process. All right, let's try another one. Again, this one's pretty much straightforward. The only difference is this is a square root function, but it's given in a bit of a different form from the other ones that we've seen. So there's just, a slightly different little change in the algebra of how it actually works out. That's good to practice and good to see. Value of a postage stamp is modeled by the function v at t equals 100 times the square root of t plus 1. Can you imagine what that graph of that would look like, thinking in transformations? So if it's a square root function, it's going like this. That means it's, I guess, which I don't know that this makes sense, but it's gaining a lot of value early on, and then the amount of value that it gains every year will decrease, which seems weird. Why would a stamp increase in value after 1 year? But anyway, that's what's happening. Okay, so V is a value and T is time in years. Determine the instantaneous rate of change of the value of the stamp at 100 years. So the value at 100 years works out to 1,001. The original value looks like it was $1. If you sub 0 in for T, it's $1. So the stamp costs $1. After 100 years, it's $1,001. Pretty expensive for a stamp. Oops. Okay, so it's pretty straightforward to get to this step. And what do we do for a square root function? What's our technique, Bradley? The conjugate. Now, I'm going to say, does anybody notice what else we could do on top here? Yeah, and I think that's a good thing to do because it's just going to make your numbers smaller. So I would common factor this first, but of course it will work out either way. So take out a common factor of 100, and you get square root of t minus 10. And then my conjugate is going to be square root of t plus 10 or square root of t plus 10.
You have to multiply 100 by it?
Nope.
Because
Because it's multiplied. Yeah. Now I can sub in, which is 100 over 10 plus 10, so 100 over 20, which is 5. Interesting. Again, don't forget to interpret your answer. What does that mean? If you have trouble with this, what I'm trying to say is force yourself to go this per this. Right? Think about what the units are, and it's this per this. Yeah, in the 100th year, the value increased by $5 per year. At that moment, the instantaneous rate of change is $5 per year. Yes. Which is 5. 100 over 2 would be 50. Yeah. Thank you. Therefore, the value of the stamp, and this is an important part of your interpretation. You don't just say, therefore the rate of change is 5, right? That's not how the statement should read. It should be interpreted in a meaningful way. The value of the stamp is increasing by $5 per year at year 100 or after 100 years. You got to say the word increasing or growing or going up or some other version of that word, not just 5. If it works out to negative, you don't just say is negative 5. You say is decreasing by a certain amount. Okay, that is paramount, absolutely necessary that you interpret what it means. Does that make sense? Everybody good? One more. So there were 2 of these from the practice on Friday, but we hadn't done one yet. It's a little bit different just because there's a pi in there. So let's see how it works out again. It pretty much always, these ones work out very similar every time. A balloon that has a perfect sphere, although again, and interpreting this and thinking about units is really strange for this one. A balloon that's a perfect sphere is being inflated by a constant flow of air. The volume of the balloon is modeled by that equation. I hope you notice that that's the volume of a sphere equation, 4/3 pi r cubed, where r is the radius in centimeters. At what rate is the volume of the balloon changing with respect to radius? So not with respect to time. A lot of the things we've done have been with respect to time. This is with respect to radius, when the radius is 10 centimeters. So as the balloon grows, as the radius grows, not thinking time, as the radius of the balloon grows, the volume will grow at a changing rate. Yeah.
If they're always a perfect circle, is the final answer always going to be the same?
No. What do you mean?
Since it's like the same, like the formula.
Same as what? Like for 10 centimeters?
Yeah.
Or for 11 or for 12, it'll be different.
Oh, really? Okay.
Yeah. Okay, so instantaneous rate of change equals the limit as r approaches 10. So let's see, we get 4 pi 10 cubed over 3. So that's 4 times 1,000, so 4,000 over 3 pi. And we want that written in terms of pi. Do not multiply that out and round it or something weird like that. You leave it there with the pi in it. That's one of the little quirks of this one, I suppose. What do you think we do here? Very good. So I can take 4 over 3 in the pi out of this one, and then I take it out of that one as well, and I'm just left with the 1,000 that we just multiplied into it. So 4 pi over 3, or 4 over 3 pi times r cubed minus 1,000, and hopefully you recognize that as a difference of cubes. Ten squared plus 10 plus 10 times 10 plus 100 is 300. Canceling that with the 3 on the bottom, or dividing that with the 3 on the bottom, I end up with 400 pi, and that is how you would leave that answer in terms of pi again. So it's exact. And what are the units?
Centimeter cubed over r.
Centimeters cubed per
Centimeter.
centimeter. That's right. It's a very strange unit. Centimeters cubed per centimeter. Sometimes it's hard when we're working with rates not to think of it in terms of time and an actual speed, but this one isn't. The volume is increasing. So for every centimeter that it increases in radius, the volume is increasing by 400 pi centimeters cubed at that instant only. But that's what it means. So 400 pi centimeters cubed per centimeter. Any questions?